Welcome to the course of Bayesian data analysis. Today we are going to talk about Bayesian analysis of Gaussian models. We already have understood that choice of prior distribution is extremely important in Bayesian data analysis. Effectively, there are three schools of thought when it comes to choice of prior distributions. First is classical Bayesian choice or classical Bayesian statisticians. For them, the prior is necessary evil. You don't want to choose your prior at all, but you want to take the advantage of Bayesian probability structure. So the choose the prior that interjects at the least information possible, typically known as the flat prior. Why this classical Bayesian consider least information, possible information should be taken through prior distribution? In 70s and 80s, when Bayesian statistics was getting slowly popularized because of the advent of computer sciences and the personal computer, at that time Bayesian statistics face a lot of criticism, particularly from scientists who more believes in objective science. By mean objective science, they believe that your science or our science should be completely data driven, and we should not incorporate our bias or societal bias in any way in the data. So, and whatever the analysis that comes through data, that should be accepted. Therefore, classical Bayesian statistician who comes from that kind of mindset, they believe that you should take a prior, but the prior should be as flat or as non-informative as possible. Modern parametric Bayesian is another approach. The prior for them is a useful convenience. Choose a prior distribution with the desirable properties, for example, conjugacy, which will give you a posterior, much more simpler form, and you can have an analytical solution. Your analysis becomes much easy to interpret. Given a distributional choice, prior parameters are chosen to interject least information possible. So you choose a prior distribution in conjugate structure, but you choose the parameters of your prior distribution in such a way so that it is as much flat as possible, and make your prior distribution almost as much flat as possible, and in that sense it will be close to a classical Bayesian approach. And a third approach is typically called a subjective Bayesian statistics. The prior is summary of old beliefs. So choose prior distribution based on the previous knowledge, either the result of earlier studies or non-scientific opinion, and you receive your data and you update your prior belief. This subjective Bayesian idea is actually turns out to be very useful in machine learning, particularly in terms of online learning. So what subjective Bayesian or subjective Bayes thinks that if you have information up to t minus 1, or whatever belief, whatever data, whatever historical data you have up to t minus 1, you develop your distribution based on information up to t minus 1, use that information to develop your prior for time point t, and then wait for data to arrive at time point t. Once the data arrives at time point t, then you update your probability distribution using posterior distribution, and then you move on. Today we will focus on Bayesian analysis of mean when variables are normally distributed and variance is also unknown. Suppose y sub I, here is our y sub I, follow normal distribution with mean mu and variance sigma square, where sigma square and mu both are unknown, but we assume they are random variable. Because if we assume mu and sigma square are random variable, then we can induce a prior on that. Note that when we were handling the binomial distribution, we had only one parameter. But here we have two parameters, and you will see it will make our life immediately little bit complicated, because when we will try to solve the problem in the denominator, we will see we have to solve a two-dimensional integration and not a one-dimensional integration. So the Bayesian setup looks like something like this. So my posterior distribution of mu sigma given y1, y2, yn. So y1, y2, yn is the data that we have observed. Follows a this is my, I can write it as a likelihood. Say this could be the likelihood of join or distribution of mu, a normal mu sigma square or mu sigma, times prior for mu and sigma. We would like to make inference about the marginal distribution of mu given y and sigma given y. So rather than the joint distribution of mu sigma given y, because mu sigma given y is not going to be very much helpful. Ultimately we would like to find something like this, probability of mu given y, and how can I get this such marginal posterior, and this is typically called marginal posterior distribution. And how can I get this marginal posterior distribution? You take the joint posterior distribution of mu sigma given y and you integrate out the sigma. If you integrate out the sigma from the joint posterior distribution of mu and sigma, what you will get the marginal posterior distribution of mu given y. Note that this marginal posterior distribution can be expressed in the following way. This is my joint posterior distribution, mu given sigma times y, sigma and y, times p of sigma given y times t sigma. I am just asking you to keep that in your mind, and this form will actually help us later in certain analysis. The y follow normal mu sigma square, where mu sigma both unknown random variable. Question turns out to be, what prior distribution would you choose to represent the absence of knowledge in these instances? What if we assume the two parameters were independent, so that p of mu sigma square, I can write it as a p of mu times p of sigma square. So is this assumption good assumption, bad assumptions? We don't know. This is some assumption that we can make, but that will make our life little bit simpler. Now how can we make that? So if we take p of mu sigma square, this is my prior distribution, and we assume mu and sigma square to be independent, and then p of mu, which makes me to write p of mu times p of sigma square. Now what I can do, I can choose p of mu to be some proportional to some constant, maybe 1, no matter what. I mean, you can choose 1 or some constant, known constant, and mu ranges for between minus infinity and infinity. Now you can, and P of sigma square you can take proportional to 1 over sigma square when the sigma square is between 0 and infinity. So the joint prior density would be P of mu sigma square is proportional to 1 over sigma square. Are these distribution proper? This is the question. So what you have to do, you have to take this distribution and integrate out and check whether integration is exist or not. If it exists, if it is integrable, then it is a proper prior distribution. Otherwise it is not a proper prior probability distribution. Now one can show, I am skipping detailed mathematics of how to derive these things, but you can show mathematically. I will point out to the book where you can see it. Some of the derivations, hint of the derivations are given, that conditional posterior distribution actually follow of mu given sigma square and y follow normal distribution y bar comma sigma square by n. And this is an interesting result, and we will, if you look at carefully, you can see that this distribution is somewhat like our sampling distribution of sample mean, like y bar follow normal mu sigma square by n. Here, as if mu and y bar have swapped their role. In the sampling distribution of sample mean, it is the y bar which follow normal mu sigma square by n. Here I am saying I know the exact value of y bar, why should I bother? Rather, what I don't know is the true value of mu, and mu is a random variable. I have some sense of value of mu which is around the y bar. That is what I am trying to say. So the marginal posterior distribution of mu, one can find out P of mu given y by integrating out the 0 to infinity P mu sigma square given y d sigma square. And if you solve this integration, it's a bit cumbersome integration, but you can solve it. If you solve this integration, it will show you that marginal posterior distribution of mu given y follow t distribution with degrees of freedom n minus 1 with location parameter y bar and a square by n. Or more conveniently, you can say square root of n mu minus y bar by sample standard deviation follow the posterior distribution follow t distribution with parameter n minus 1. So this is also, so this is what we are trying to say here, that my posterior distribution turns out to be exactly like sampling distribution of y bar if I choose this particular prior. If I choose this particular prior, then posterior distribution of mu behave exactly same like sampling distribution of y bar. Similarly, my marginal posterior distribution of mu will exactly behave like sampling distribution of y bar when you are estimating standard deviation by sample standard deviation. So that means effectively my Bayesian analysis will exactly match with my classical textbook analysis or frequentist analysis. Now, why should I then bother to do Bayesian analysis? You can ask me. The answer is that if I choose this particular prior, then my exact analysis is same as the classical textbook Bayesian frequentist analysis. major advantage is now I can make direct probabilistic statement, whereas in the classical frequentist analysis my statements will be much more convoluted and implicit. The probability statement in the classical textbook analysis is much more implicit and convoluted. It is very difficult to convince layman people, where if you are talking to a policymaker who has you know some exposure to statistics, some introductory statistics, but not much. If you tell them what is the confidence interval inference, what is the p-value, they take it. But my experience is, if you just give them a probabilistic statement, that is much, people appreciate that kind of analysis much more, or that kind of probabilistic statement much more, particularly the practitioner. So this Bayesian analysis actually a lifesaver for statistician, because this is a choice of prior. This prior choice gives me Bayesian analysis which exactly match with the classical frequentist statistical analysis. In addition, it gives me the advantage of the way the direct probabilistic statement that I want to make, I can make now. So you can show that the marginal posterior distribution of sigma square follows scaled inverse chi-square distribution. So you can now take this mu joint probability distribution of mu posterior probability distribution of mu sigma square given y bar a square, and you integrate out the mu, then what you will get is the marginal posterior distribution of sigma square. And the interesting thing is, if you can actually analytically solve this integration. I am not making you go through this very cumbersome integration, but the final result, one can show that the sigma square given y follow inverse chi-square distribution with n minus 1 degrees of freedom with a square as the central x parameter. Or one can show that this inverse chi-square is actually also inverse gamma with n minus 1 by 2 and n minus 1 a square by 2. So this is also actually similar to the sampling distribution of sigma square in the classical distribution setup, classical statistics setup. Big point to note here that though prior is flat and improper, remember that my prior is flat, I have no information about the mu and sigma square. The posterior is a proper prior probability distribution. Hence, a proper statistical inference can be drawn from it. So let me go back a couple of slides before. So this was my joint prior distribution, remember that. And if you integrate out, it will never be one, or it will never be a constant. So that means this prior distribution is not a proper probability distribution. Hence, you cannot use this prior distribution at all to make any kind of probabilistic statement about mu and sigma square. It is useless. Effectively, it is useless. But my posterior distributions of mu and sigma square turns out to be proper probability distribution, so I can make proper statistical inference, and turns out these statistical inference exactly match with, analytically and numerically exactly match with, not analytically but rather numerically match with the classical frequentist statistics. And it gives me the advantage of simple interpretation, making simple probabilistic statement about the parameter mu, about the mean and variance, about the of the distribution. Now I am going to move on to next approach called parametric Bayesian approach, and we are going to use the conjugate prior distribution. So if denote the class of density where the actual data model f of x given theta belongs to, theta is the parameter index, typically it is being indexed by theta. A class of prior distribution is said to be conjugate family if the posterior also belongs to the same class. So that means, like in the beta binomial distribution, we found when we choose a prior distribution, beta prior distribution on the sample proportion, it turns out the posterior distribution is also beta distribution, and that gives us a lot of flexibility in terms of analytical properties. We know all the analytical properties of the beta distribution, so we can directly use those formulas from our textbook to solve any standard application problem. Similarly, similar approach we can apply in the Gaussian model problem as well. Here I have provided a list of conjugate prior for different kind of data models. If x follow normal distribution with parameter theta and sigma square, and theta is unknown and sigma square is known, suppose you know the value of sigma square, then you can just choose theta follow normal distribution with some parameter mu m and s square. Then if you take the opposite problem, the x follow normal distribution, but now mu is known, your mean is known, but you treat that sigma theta is unknown, then you can choose theta to be inverse gamma with parameter alpha beta. And then x, if it follows Poisson distribution with parameter theta unknown, you can choose theta to be gamma alpha beta. If x follow binomial n theta, n is known and theta unknown, theta is sample proportion, then theta you can choose beta alpha beta. Similarly, if x follow gamma nu theta and theta unknown and nu is known, then you can choose theta as gamma alpha beta. So these are the some of the models for which we know what are the conjugate priors, and these conjugate priors are actually gives us a lot of advantage, and these are often used to solve many problems. Now we will check how parametric Bayesian used conjugate prior to solve problem of the normal distribution with mu sigma square with when both mu and sigma square are unknown, and we want to induce a prior, some sort of conjugate prior on mu and sigma square. Interestingly, you will see that there is mu, support of mu is between minus infinity and plus infinity, and sigma square is between 0 and infinity. And we do not know any distribution in the two-dimension space which has this kind of support, that one variable is on the minus infinity to infinity, another variable on the sigma like 0 to infinity. We don't know any distribution, so we cannot, if we had a distribution, we can check whether that can be used as a conjugate prior. So we have to use the known these two information, that when I know sigma square or the variance, my theta I can assume normal mu sigma square, and when I know mu and I don't know about the sigma, and I can consider inverse gamma as conjugate prior on the variance, these informations we can use to model when the both mu and sigma square are unknown and we want to model this situation. This approach is typically called normal inverse chi-square distribution, and this is defined as with I think 1, 2, 3, 4 parameters. with four parameters. So how we do that? We call it P of mu sigma square, the joint distribution of mu sigma square. We model it as mu given sigma square times P sigma square. Now, mu given sigma square, we model it as normal mu 0 sigma square by k0. This is, I'm treating as if I know the sigma square, and then the sigma square, I just put an inverse chi-square distribution with degrees of freedom nu 0 sigma 0 square. So there are four hyperparameters, this mu 0, k0, nu 0 and sigma 0 square. Exact posterior distribution we can solve it by hand, but again I'm skipping that manual complex derivation of mu, what is the posterior distribution of mu sigma square given y. That turns out to be mu sigma square given y, this is the joint posterior distribution of mu sigma square, has exact same probabilistic structure just like its prior distribution. Like it is normal inverse chi-square with, instead of mu 0 we have an updated mu n, instead of sigma 0 by k0 we have a now updated sigma n square by kn, instead of nu 0 I have updated parameter nu n, and sigma 0 square I have updated by sigma n square, and these parameters are something like that. Mu n is k0 by k0 plus n times mu 0 plus n by k0 plus n y bar. Kn is k0 plus n, nu n is nu 0 plus n, and nu n sigma n square is nu 0 sigma 0 square plus n minus 1 a square plus k0 plus n times n by k0 plus n y bar minus mu 0 square. Big point to note here, here the prior is proper. So the prior distribution is proper, hence posterior is proper probability distribution, hence proper statistical inference can be drawn from it. Now I am making a big statement. If prior is proper distribution, then posterior will always be proper. But if prior is improper, then posterior is not necessarily proper. And this statement, this is actually a result. You can prove this result. At least this result, if prior distribution is proper, then posterior will always be proper. You can prove this result. I am leaving it as an assignment. But if prior is improper, then if the prior is improper, then posterior will be proper or not. There is no such theorem or result is there. So we cannot really say that if the prior is improper, then posterior will be improper. We have already have seen a case that prior is improper and turns out to be posterior distribution is proper for this choice. If we go back, the first choice of prior, this choice here, this prior was improper, but turns out our posterior was proper, right? But there are cases, for example, in the logistic distribution, if on the parameter space, if you take an improper prior, it turns out to be the posterior distribution is not proper. Posterior distribution is improper. So you have to be a bit careful if you decide to use an improper prior. So not necessarily it will give you a proper prior distribution, and if it does not give you a proper prior distribution, then you end up with something which is not a valid statistical inference. Because if your posterior distribution is not a proper probability distribution, then your inference is completely invalid. You cannot make any valid statistical inference, nobody will accept your statistical analysis. So whenever you are doing a Bayesian data analysis, you have to make sure the posterior distribution that you are using a proper probability distribution. If your posterior distributions are not proper probability distribution, if you cannot guarantee that and turns out to be it is a improper letter, then it's a big problem, and that means all the statistical analysis are not acceptable in any academic community. So you have to be very careful when you're using improper prior. You just make sure the improper prior that you are using, some academic paper, some book somewhere has showed that the corresponding posterior distribution is proper. That means otherwise you should not use improper prior distribution for which you don't know whether if the posterior is proper. Now let's move on to a application. The application is, so what is the average blood pressure reading of a subpopulation of say 20 adult men? So you have randomly sample 20 adult men, and you have collected their blood pressure, and suppose y sub I denote the blood pressure of individual I, and assume that yi follow some normal distribution. So mu denote the average blood pressure of the group. Thus I can assume yi follow normal mu sigma square. Sample average turns out to be, suppose y bar is 128 and the sample standard deviation is S 7.67. It is given. You can immediately calculate. I know that marginal posterior distribution mu given y under improper prior of 1 by sigma square is T distribution n minus 1 y bar S square by n. And expected value of this distribution is y bar. So my Bayesian estimate is exactly sample estimate, and variance of mu given y is S square by n minus 2, so 3.27. Now what I can do, I can also simulate mu from T n minus 1 y bar S square by n and take the average, and turns out the average is 128 and median is also 128. I have simulated about 1000 samples, and variance of mu turns out to be 3.28, which is approximately close to 3.27. Standard deviation of mu is 1.812, and the confidence interval, 95% confidence interval of mu is somewhere between 124.39 and 131.56. Now let's look into what happens with the flat prior also. So how the marginal distribution of sigma square behaves. So the sigma square, we know that posterior marginal distribution of sigma square given y follow inverse chi-square distribution with degrees of freedom n minus 1 S square. By the properties of scale inverse chi-square distribution, one can find, you can just take a textbook and plug in, and from the textbook you will get this expected value of the scale inverse chi-square distribution. Expected value of, you can, I think in Gelman's book, which is a textbook for this course, at the end has given all the list of distributions where their mean and variance. So you can just consult the Gelman's book on Bayesian data analysis. Has all these formulas actually. Expected value of sigma square given y is equal to S square n minus 1 by n minus 3, 64.9, and square root of expected value of sigma square given y will give you 8.06. Now the disadvantage of using improper prior is if I have some expert's opinion and I cannot use model the expert's opinion or incorporate the expert's opinion in my analysis. So somebody, may say that, okay, I have only 10, 20 patient for which I have this data, and I don't have enough patient to make a really confident answer. So, but I know there are a lot of doctors who have 30 years of experience, 40 years of experience. Can I incorporate that expert's opinion in my model? There are a lot of rare disease where you do not have more than maybe 10 or 15 patients. So that means effectively your sample size is only 10 or 15, 1 5, and naturally your confidence on your analysis will be much less. Your all confidence interval will be much bigger, much larger. Now, if you have a doctor who has a 40 years of experience, and would you not like to incorporate that expert's opinion about certain parameters of the patients into your analysis? If you're okay with that, then suppose we agree philosophically, we agree that yes, we should incorporate that doctors or the experts' opinion within our analysis. At least no harm trying it out, whether to see much it, how much the experts' opinion uh, is with the data and or far away from the data. So experts believe, suppose in this particular application, it's a simple application, average blood pressure would be in the range of 110 and 130, with most confident region would be around 120. A suitable prior model for experts view is for average blood pressure will be mu follows say some mu square sigma square by k0. So where mu 0 equal to 120, okay, and sigma square is around 5 square. So it is sigma 0 is sort of a standard deviation, so 2 times of the standard deviation will make it about 95% of the confidence interval. So one about 95% of the confidence is between 110 and 130, so that makes it sigma square to be near 5, and I'm k0 equal to 1, that is only suppose we are considering taking only one data points of the number of expert, as if k0 is the number of experts you have in your model. So suppose we have only one expert in our model, and now sigma square inverse chi square, where nu 0 equal to 1 indicate the degrees of freedom, which now if you take nu 0 equal to 1, which actually inverse of impose a Cauchy prior on mu, turns out, and sigma 0 equal to 5. So that means the induced prior on the mu will be a Cauchy prior, so it will be a proper probability distribution, but which mean variance does not exist. So this is a very interesting, and Cauchy prior turns out to be a very useful prior. Cauchy distribution turns out to be a very useful prior when if you want to model some mean or coefficients and many parameters. So by the properties of t distribution, we have this we have these results, analytical results. Let me go back, and we have this formula. We have solved this posterior distribution. Now if I come back, expected value of mu given y is mu n, which is k0 by k0 plus n times mu 0, and n over k0 plus n times y bar. Now if you plug it in, turns out to be 127.62. So y bar was 128. So it is my posterior. I started with a prior mean 120. Now after updating, now my posterior mean has gone very close to 128. Now here an interesting thing you see, if you look into this formula, so mu 0 is my prior mean and y bar is my sample mean, and k0 by k0 plus n and n by k0 plus n is the sort of weights, and so my posterior mean is effectively the weighted average of my prior mean and sample mean. And this posterior mean, it tend to be always somewhere between prior mean and the sample mean. This tells us, and naturally if you have lot of samples, then posterior mean will be close to your sample mean, whereas if you have less sample, then accordingly weight will be adjusted. And nu n sigma n square, if you just take this formula again and you just plug those values, turns out to be 1203.7, and then variance of mu given y, if you just nu n sigma n square you is 1203.7, and then you plug these values, it turns out to be 3.08. Now again, if you solve this problem, you can either, we have this is our analytical results, and you can also solve this problem numerically by simulating mu's and sigmas from the posterior distribution, and turns out to be this is very close to 3.015. if you round it off to 3.02, this is the value, and 127.62 is the result, and turns out to be this is 128 and 128, which is close to the, posterior mean is close to this numerical mean is close to this one, analytical mean. So I'll stop here, and now we will move on to the hands-on, and we will do the hands-on in the next session. Thank you very much.